Chapter 4 Threads. A thread refers to the smallest unit of execution within a process. A process can have multi-threaded and each threads can execute different tasks concurrently. Threads share the same resources of the process such as memory space, but they have their own separate execution flow. Using threads allow program to perform multiple tasks simultaneously, which can lead to better performance and responsiveness in certain applications. However, managing threads can be complex as developer needs to handle issues like synchronization and data sharing between threads to avoid conflict and ensure correct execution. Here we have two types of threaded process: single threaded process and multi-threaded process. A single threaded process is a type of process that run only one thread of execution at a time. In other words, the process execute tasks sequentially one after another without any concurrency or parallelism. This means that it can only perform one operation at a time and any other task have to wait until the correct task is completed. Single threaded processes are generally straightforward to implement and manage because there are no concern about synchronization or data sharing between threads. However, they may not fully utilize modern multi-core process since they can't take advantage of parallel processing. Next one is a multi-threaded process. A multi-threaded process is a program or application that utilizes multiple threads to perform tasks concurrently within a single process. Unlike single-threaded process that can only execute one instruction at a time, multi-threaded process can divide their workload among multiple threads, allowing for better resource utilization and improved performance. A multi-threaded process, each thread operates independently and can execute different parts of the program. This parallel execution can lead to increased efficiency, especially in tasks that can be divided into smaller subtasks. However, managing multi-threaded process requires carefully consideration of synchronization and potential data conflict. Developers need to use synchronization mechanism like locks or semaphores to ensure threads interact correctly and avoid race condition. Multi-threaded is particularly beneficial in applications that involve I/O operation or user interface, as it allows these processes to remain responsive while handling various tasks concurrently. The programming multi-threaded application can be more challenging. Here we have some benefits of multi-threaded programming. Here we have 4 benefits. First one, responsiveness; second, resource sharing; third, economic; and fourth one, utilization of multi-process architectures. First one, responsiveness. Threading an interactive application may allow a program to continue running even if part of it is blocked or it performing a operation, thereby increasing responsiveness to the user. For instance, a multi-threaded web browser could allow user interaction in one thread while an image was being loaded in another thread. Second one is a resource sharing. Process may only share resources through technique such as shared memory or message passing. Such technique must be explicitly arranged by the programmer. However, threads share the memory and the resource of the process to which they belong by default. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. Third one is the economy. Allocating memory and resources for process creation is costly because threads share the resources of the process to which they belongs. It is more economically to create and context switch threads. Empirically, the difference in overhead can be difficult, but in general, it is much more time consuming to create and managing process the thread than threads. Fourth one is a utilization of multiprocessor architectures. The benefits of multi-threading can be greatly increased in a multiprocess architecture where thread may be running in a parallel on different processes. A single threaded process can only run one on one CPU no matter how many are available.
So in this session, we are going to learn multi-threading models. So multi-threading models support for threads may be provided either at user level for user threads or by the kernel for kernel threads. There must be a relationship between user threads and a kernel threads. Three common ways of establishing this relationship are: first one is of many to one. Many to one user level threads are mapped to single kernel threads as shown in a figure. So we can refer to a 4.2 diagram in a textbook. So in this model, a model is efficient as a thread management is done by a thread library in a user space, but the entire process will block if the thread makes a blocking system call, as only one thread can access the kernel thread at a time. Multiple threads are unable to run in a parallel on multiprocesses. So for example, we can take a Solaris's green threads and GNU portable threads. So as we all know, a multiple threads are unable to run in a parallel on multiprocesses. So in multi-threading models, the next one is of one-to-one. So in this one-to-one, each user level threads maps to kernel threads as shown in a figure 4.3 in a textbook. It provides more concurrency than many to one model by allowing threads to run when a thread makes a blocking system call. It allows multiple threads to run in a parallel on multiprocesses. The only drawback is creating a user thread requires creating the corresponding kernel thread and it burdens performance of an application. Examples: Windows NT, XP 2000 and Linuxes. So in multi-threading models, the third one is of many-to-many models. So in this many-to-many models, the first point is of one-to-one model restricts creating more user threads and many-to-many model allows creating more user threads, but kernel can schedule only one thread at a time. These drawbacks can overcome by many-to-many models as shown in a figure. So we can consider a 4.4 diagram in a textbook. So it says that many-to-many model allows many user threads to be mapped to many kernel threads. It allows the operating system to create a sufficient number of kernel threads. When thread performs a blocking system call, the kernel can schedule another thread for execution. It allows user level threads to be bound to a kernel thread, and this is referred as a two-level model as shown in a figure. So the examples are IRIX, HPUX and Solaris of OS. So the next one is of thread libraries. In a thread libraries, it provides a programmer an API for creating and managing threads. It allows a user level thread to be bound to a kernel thread, and this is referred as two-level model as shown in a figure 4.5 diagram in a textbook. So there are two primary ways for implementing a thread library. So the first approach is to provide a library entirely in a user space with no kernel support. All code and data structure for a library exist in a user space. So the second approach is to implement a kernel level library supported directly by the operating system. So the three primary thread libraries are POSIX, pthreads. So it stands for Portable Operating System Interface. So it is the extension of a POSIX standard. They may be provided as either a user board kernel libraries. So the second one is of Win32 thread. It is a kernel level library available on a Windows system. So the third one is of Java thread. API allows creation and management directly in a Java programs. However, on Windows, Java thread are implemented using Win32 and on Unix and Linux using pthreads. So the next one is of pthreads. So pthreads are an extension of a POSIX standard may be provided as either a user or kernel level library. So pthread refers to a POSIX standard defining an API for thread creation and synchronization. So now we can consider a 4.6 in a textbook. It is of a multi-threaded C programming using a pthread API. So in this, a program has two threads, the initial thread in main function and the summation thread performing the summation operation in a runner function. After creating the summation thread, a parent thread will wait for it to complete by calling the pthread join. The summation thread will complete when it calls the function pthread. Once the summation thread has returned, the parent thread will output the value of the shared data sum. So it is a specification of a thread behavior, not an implementation. Operating system designers may implement a specification in any way they wish. Numerous systems implement a pthread specification, including Solaris, Linux, Mac OS, and True64 Unix. Shareware implementations are available in a public domain for the various Windows operating system as well.
This is a multi-threaded C program using the Win32 API. It makes the summation of a non-negative integer and shows us how threads are handled, how multi-threading is possible by using the Win32 API. Next, we move on to Java threads. Threads are the fundamental model of program execution in a Java program. The Java language and its API provide a rich set of features for the creation and management of threads. All Java programs comprise of at least a single thread of control. Even in a simple Java program consisting of only a main method runs as a single thread in a JVM. There are two techniques for creating threads in a Java program. One approach is to create a new class that is derived from the thread class and override its run method. An alternatively, or more commonly used method, technique is used to define a class that implements the runnable interface. The runnable interface is defined as follows: public interface runnable, public abstract void run. When a class implements runnable, it must define a run method. The code implementing the run method is what runs a separate thread. Figure 4.8 shows the Java version of a multi-threaded program that determines the summation of a non-negative integer. The summation class implements the runnable interface. The thread creation is performed by creating an object instance of the thread class and passing the constructor a runnable object. Creating a thread object does not specifically create a new thread. Rather, it is the start method that actually creates the new thread. Calling the start method for the new object does two things. One, it allocates memory and initializes a new thread in the JVM. Two, it calls the run method, making the thread eligible to be run by the JVM. Note that we never call the run method directly. Rather, we call start method and it calls the run method on our behalf. When the summation program runs, two threads are created by the JVM. First is the parent thread, which starts execution in the main method. The second thread is created when the start method on the thread object is invoked. This child thread begins execution in the run method of the summation class. After outputting the value of summation, This thread terminates when it exits from the run method. Sharing of data between threads occurs easily in Win32 and P threads, as shared data are simply declared globally. As a pure object-oriented language, Java has no such motion of global data. If two or more threads are to share data in a Java program, the sharing occurs by passing a reference to the shared object to the appropriate threads. In the Java program shown in figure 4.8, the main thread and the submission thread share the object instance of the sum class. This shared object is referenced to the appropriate getSum and setSum methods. You might wonder why we don't use an integer object rather than designing a new sum class. The reason is that the integer class is immutable. That is, once its value is set, it cannot change. Recall that the parent threads in the pthreads and the Win32 libraries use pthread underscore join and wait for single object respectively to wait for the summation threads to finish before proceeding. The join method in Java provides similar functionality. Notice that the join method can throw an interrupted exception, which we can choose to ignore. This is the Java program for the summation of a non-negative integer. We create a class sum and then we create a class summation which implements the runnable interface to be able to create new threads. Then we have a public class driver which runs the program. And the main program is inside the public class driver. We also have a try catch exception block which catches the interrupted exception of join and which we choose to ignore. The entire program is for the summation of a non-negative integer. JVM and host operating system. The JVM is typically implemented on top of a host operating system. This setup allows the JVM to hide the implementation details of the underlying operating system and to provide a consistent abstract environment that allows Java programs to operate on any platform that supports a JVM. The specification for the JVM does not indicate how Java threads are supposed to be mapped to the underlying operating system, instead leaving the decision to the particular implementation of the JVM. For example, the Windows XP operating system uses the one-to-one model. Therefore, each Java thread for a JVM running on such a system maps to a kernel thread. On operating systems that use the many-to-many model, such as True64 Unix, a Java thread is mapped according to the many-to-many model. Solaris initially implemented the JVM using the many-to-many model. Later releases of the JVM were implemented using the many-to-many model. Beginning with Solaris 9, Java threads were mapped using the one-to-one model. In addition, there may be a relationship between the Java thread library and the thread library of the host operating system. For example, the implementations of a JVM for the Windows family of operating systems might use the Win32 API when creating the Java threads. Linux and Solaris systems might use the pthreads API.
Threading issues. In this session, we discuss some of the issues to consider with multi-threaded programs. The fork and execute system calls. In chapter 3, we described how the fork system call is used to create a separate duplicate process. The semantic of fork and execute system calls in multi-thread programs. If one thread in a program calls a fork, does the new program duplicates all threads, or is the new process single-threaded? Some Unix systems have chosen to have two versions of fork, one that duplicates all threads and other one that duplicates only the thread that invoke the fork system call. In execute system call typically works in some way as described in chapter 3. That is, if a thread invokes execute system call, the program specified in a parameter to execute will replace the entire process, including all threads. Which of the two versions of fork to use depends on applications. If execute is called immediately after forking, the duplicating of all threads is unnecessary, as program specified in the parameter to execute will replace the process. In this instance, duplicating only the calling thread is inappropriate. If, however, the separate process does not call execute after forking, the separate process should duplicate all threads. Thread cancellation is a task of terminating a thread before it is complete. For example, if a multiple thread is concurrently searching throughout a database and one thread returns the results, the remaining threads might be cancelled. Another situation might occur when a user presses a button on a web browser that stops a web page from loading any further. Often, a web page is loaded using server threads. Each image is loaded in a separate thread. When a user presses a stop button on the browser, all threads loading the page are cancelled. A thread that is cancelled is often referred as a target thread. Cancellation of a target thread may occur in two different scenarios. Asynchronous cancellation. One thread immediately terminates the target thread. Deferred cancellation. The target thread periodically checks whether it should terminate, allowing it an opportunity to terminate itself in an orderly fashion. The difficulty with cancellation occurs in situations where resources have been allocated to a cancel thread, or where a thread is cancelled while in the midst of an updating data. It is sharing with other threads. This becomes especially troublesome with asynchronous cancellation. Often, the operating system will reclaim system resource from a cancelled thread but will not reclaim all the resource. Therefore, cancelling a thread asynchronously may not free a necessary system-wide resource. With deferred cancellation, in contrast, one thread indicates that a target thread is to be cancelled. But cancellation occurs only after the target thread has checked a flag to determine if it should be cancelled or not. This allows a thread to check whether it should be cancelled at a point when it can be cancelled safely. PT threads refer to such points as cancellation points. Signal handling. A signal is used in Unix systems to notify a process that particular event has occurred. A signal may be received either synchronously or asynchronously, depending on the source and the reason for the event being signaled. All signals, whether synchronously or asynchronously, follow some pattern. Number one, a signal is generated by the occurrence of a particular event. Number two, a generated signal is delivered to a process. Number three, once delivered, the signal must be handled. Examples of synchronous signals includes legal memory access and division by zero. If a running program performs either of these actions, a signal is generated. Synchronous signals are delivered to the same process that performed the operation that caused the signal. That is the reason they are considered synchronous. When a signal is generated by an event external to a running process, that process receives the signal asynchronously. Examples of such signals include terminating a process with specific keystrokes and having a timer expire. That typically an asynchronous signal is sent to another process. Every signal may be handled by one of two possible handlers. Number one, a default signal handler. Number two, a user defined signal handler. Every signal has a default signal handler that runs by the kernel when handling that signal. This default action can be overridden by a user defined signal handler that is called to handle the signals. Signals may be handled in different ways. Some signals, such as changing the size of windows, may be simply be ignored. Others, such as an illegal memory access, may be handled by terminating the program. Handling signals in a single threaded program is straightforward. Signals are always delivered to a process. However, delivering signals is more complicated in multi-threaded programs, where a process may have server threads where then should a signal be delivered? In general, the following options exist. Number one, deliver the signal to a thread to which the signal applies. Number two, deliver the signal to every thread in the process. Number three, deliver the signal to certain threads in the process. Number four, assign a specific thread to receive all signals for the process. The method for delivering a signal depends on type of signal generated. For example, synchronous signals need to be delivered to a thread causing the signals and not to other threads in the process. However, the situation with asynchronous signal is not a clear. Some asynchronous signals, such as signals that terminate a process, should be sent to all threads. Most multi-threaded versions of Unix allow a thread to specify which signals it will accept and which it will block. Therefore, in some cases, as asynchronous signal may be delivered only to those threads that are not blocking it. However, because signals need to be handled only once, a signal is typically delivered only to the first thread. found that it is not blocking it. The standard unique functions for delivering a signal is killed. Here, we specify the process to which a particular signal is to be delivered. However, POSIX pthreads also provide the pthread kill function that will allow a signal to be delivered to a specific thread. Although Windows does not explicitly provide support for signals, they can be emulated using asynchronous procedure calls APCs. The APC facilitate allows a user thread to specify a function that is to be called when the user thread receives notification of a particular event. As indicated by its name, the APC is roughly equivalent to an asynchronous signal in Unix. However, whereas Unix must be content with how to deal with a signal in a multi-threaded environment, the APC facility is more straightforward, as APC is delivered to a particular thread rather than a process.
Thread pools. In section 4.1, we mentioned multithreading in a web server. In this situation, whenever the server receives a request, it creates a separate thread to service the request. Whereas creating a separate thread is certainly superior to creating a separate process. A multi-threaded server nonetheless has potential problems. The first concerns the amount of time required to create the thread prior to servicing the request, together with the fact that this thread will be discarded once it has completed its work. The second issue is more troublesome. If we allow all concurrent requests to be serviced in a new thread, we have not placed a bound on the number of threads concurrently active in the system. Ultimately, threads could exhaust system resources such as CPU time or memory. One solution to this issue is to use a thread pool. The general idea behind a thread pool is to create a number of threads at process startup and place them into a pool where they sit and wait for work. When a server receives a request, it awakens a thread from this pool. If one is available, and passes it the request to service. Once the thread completes its service, it returns to the pool and awaits more work. If the pool contains no available thread, the server waits until one becomes free. Thread pools offer some benefits, like servicing a request with an existing thread is usually faster than waiting to create a thread. A thread pool limits the number of threads that exist at any one point. This is particularly important on systems that cannot support a large number of concurrent threads. The number of threads in the pool can be set hysterically based on factors such as the number of CPUs in the system, the amount of physical memory, the expected number of concurrent client requests. More sophisticated thread pool architectures can dynamically adjust the number of threads in the pool according to usage patterns. Such architectures provide the further benefit of having a smaller pool, thereby consuming less memory when the load on the system is low. The Win32 API provides several functions related to thread pools. Using the thread pool API is similar to creating a thread with the thread create function as described in the section 4.3.2. Here, a function that is to run as a separate thread is defined. Such a function may appear as follows. A pointer to pool function is passed to one of the functions in the thread pool API, and a thread from the pool executes this function. One such member in the thread pool API is the queue user work item function, which is passed three parameters. First, LP thread start routine function, a pointer to the function that is to run a separate thread. P void param, the parameter passed through function. U long flags, flags indicating how the thread pool is to create and manage execution of the thread. An example of an invocation is given below. This causes a thread from the thread pool to invoke pool function on behalf of the programmer. In this instance, we pass no parameters to pool function because we specify 0 as a flag. We provide the thread pool with no special instructions for thread creation. Other members in the Win32 thread pool API include utilities that invoke the function at periodic intervals or when a synchronous input-output request completes. The java.util concurrent package in Java 1.5 provides a thread pool utility as well. Thread-specific data. Threads belonging to a process share the data of the process. Indeed, this sharing of data provides one of the benefits of multi-threaded programming. However, in some circumstances, each thread might need its own copy of certain data. We will call such data thread-specific data. For example, in a transaction processing system, we might service each transaction in a separate thread. Furthermore, each transaction may be assigned a unique identifier. To associate each thread with its unique identifier, we could use thread-specific data. Most thread libraries, including Win32 and pthreads, provide some form of support for thread-specific data. Java provides support as well. Scheduler activations. A final issue to be considered with multi-threaded programs concerns communication between the kernel and the thread library, which may require by the many-to-many and two-level models discussed in section 4.2.3. Such coordination allows the number of kernels thread to dynamically adjust to help ensure the best performance. Many systems implementing either the many-to-many or two-level models place an intermediate data structure between the user and the kernel threads. This data structure, typically known as lightweight process or LWP, is shown in the figure 4.9. To the user thread library, the LWP appears to be a virtual processor on which the application can schedule a user thread to run. Each LWP is attached to the kernel thread and is kernel thread that the operating system schedules to run on particular, that is, physical processes. If a kernel thread blocks, such as while waiting for an input-output operation to complete, the LWP blocks as well. Up the chain, this user-level thread attached to the LWP also blocks. Here, in the figure 4.9, lightweight processes, that is LWP, are shown. An application may require any number of LWPs to run efficiently. Consider a CPU-bound application running on a single processor. In this scenario, only one thread can run at once. So, one LWP is sufficient. An application that is input-output intensively may require multiple LWPs to execute. However, typically an LWP is required for each concurrent blocking system call. Suppose, for example, that 5 different file read requests occur simultaneously. 5 LWPs are needed because all could be waiting for input-output completion in the kernel. If a process has only 4 LWPs, then the 5th request must wait for one of the LWPs to return from the kernel. One scheme for communication between the user thread library and the kernel is known as scheduler activation. The works as follows. The kernel provides an application with a set of virtual processors, that is LWPs, and the application can schedule user threads onto an available virtual processor. Furthermore, the kernel must inform an application about certain events. This procedure is known as an upcall. Upcalls are handled by the thread libraries with an upcall handler, and upcall handlers must run on a virtual processor. One event that triggers an upcall occurs when an application thread is about to block. In this scenario, the kernel makes an upcall to the application, informing it that a thread is about to block and identifying the specific thread. The kernel then allocates a new virtual processor to the application. The application runs an upcall handler on this new virtual processor, which saves the state of the blocking thread and relinquishes the virtual processor on which the blocking thread is running. The upcall handler then schedules another thread that is eligible to run on the new virtual processor. When the event that the blocking thread was waiting for occurs, the kernel makes another upcall to the thread library, informing it that the previously blocked thread is now eligible to run. The upcall handler for this event also requires a virtual processor, and the kernel may allocate a new virtual processor or preempt one of the user threads and run the upcall handler on its virtual processor. After making the unblocked thread as eligible to run, the application schedules an eligible thread to run on an available virtual processor.
4.5 Operating System Examples. In this section, we explore how threads are implemented in the Windows XP and Linux systems. Windows XP threads. Windows XP implements the Win32 API. The Win32 API is the primary API for the family of Microsoft operating systems: Windows 95, 98, NT, 2000, and XP. Indeed, much of what is mentioned in this section applies to this entire family of operating systems. A Windows XP application runs as a separate process, and each process may contain one or more threads. The Win32 API for creating threads is covered in section 4.3.2. Windows XP uses the one-to-one mapping described in section 4.2.2, where each user level thread maps to an associated kernel thread. However, Windows XP also provides support for a fiber library, which provides the functionality of the many-to-many model, section 4.2.3. By using the thread library, any thread belonging to a process can access the address space of the process. The general components of a thread include a thread ID uniquely identifying the thread, a register set representing the status of the processor, a user stack employed when the thread is running in user mode, and a kernel stack employed when thread is running in kernel mode, a private storage area used by various runtime libraries and dynamic link libraries. The register set, stacks, and private storage area are known as the context of the thread. The primary data structures of a thread include E-thread, executive thread block; K-thread, kernel thread block; TEB, thread environment block. The key components of the E-thread include a pointer to the process to which the E-thread belongs and the address of the routine in which the thread starts control. The E-thread also contains a pointer to the corresponding K-thread. The K-thread includes scheduling and synchronization information for the thread. In addition, the K-thread includes the kernel stack used when the thread is running in the kernel mode and a pointer to the TEB. The E-thread and K-thread exist entirely in kernel space. This means that only the kernel can access them. The TEB is a user space data structure that is accessed when the thread is running in user mode. Among other fields, the TEB contains the thread identifier, a user mode stack, and an array for the thread specific data, which Windows XP terms thread local storage. The structure of a Windows XP thread is illustrated in figure 4.10. Linux threads. Linux provides the fork system call with the traditional functionality of duplicating a process as described in chapter 3. Linux also provides the ability to create threads using the clone system call. However, Linux does not distinguish between processes and threads. In fact, Linux generally uses the term task rather than process or thread when referring to a flow of control within a program. When close is invoked, it is passed a set of flags which determine how much sharing is to take between the parent and the child tasks. Some of these flags are listed below. Flag meaning clone fs, file system information is shared. Clone VM, the same memory space is shared. Clone sighand, signal handlers are shared. Clone files, the set of files, open files is shared. For example, if clone is passed, the flags clone fs, clone VM, clone sighand, and clone files, the parent child and tasks will share the file system information, such as the current working directory and the same memory space, the same signal handlers, and the same set of open files. Using clone in this fashion is equivalent to creating a thread as described in this chapter, since the parent task shares most of its resources with its child task. However, if none of these flags are set when clone is invoked, no sharing takes place, resulting in functionality similar to that provided by the fork system call. The varying level of sharing is possible because of the way a task is represented in Linux kernel. A unique kernel data structure, specifically struct task struct, exists for each task in the system. This data structure, instead of storing data for the task, contains pointers to other data structures where these data are stored. For example, data structures that represent the list of open files, signal handling information, and a virtual memory. When fork is invoked, a new task is created along with a copy of all associated data structures of the parent process. A new task is also created when the clone system call is made. However, rather than copying all data structures, the set of new task points to the data structures of the parent task depending on the set of flags passed to clone. 4.6 Summary. A thread is a flow of control within a process. A multi-threaded process contains several different flows of control within the same address space. The benefits of multi-threading include increased responsiveness to the user, resource sharing within the process, economy, and the ability to take advantage of multiprocessor architectures. User level threads are threads that are visible to the programmer and are known to the kernel. The operating system kernel supports and manages kernel level threads. In general, user level threads are faster to create and manage than kernel threads, as no intervention from the kernel is required. Three different types of models relate user and kernel threads. The many to one model maps many user threads to a single kernel thread. The one to one model maps each user thread to a corresponding kernel thread. The many to many model multiplexes many user threads to a smaller or equal number of kernel threads. Most modern operating systems provide kernel support for threads. Among these are Windows 98, NT, 2000, and XP, as well as Solaris and Linux. Thread libraries provide the application programmer with an API for creating and managing threads. Three primary thread libraries are in common use: POSIX pthreads, Win32 threads, and Windows systems and Java threads. Multi-headed programs introduce many challenges for the programmer, including the semantics of the fork and execute system calls. Other issues include thread cancellation, signal handling, and thread specific data. That was Chapter 4 on threads, presented by Shireen, Shreyas, Shreyash, Shreyamsh, Vasudha, and Vasundhara. Thank you.